Hello everybody, my name is Mihailo Obrenovic and I'm coming from ICube laboratory. And today I'm going to present about my work on semantic heterogeneous domain adaptation with vision language models in remote sensing. Small outline of today's talk. So first I will describe heterogeneous domain adaptation. Then I will talk about vision language models. Then we will see how we can use these two together for two different cases. So like I present the solution in one case where it was successful, and then I discuss some future work and challenges in a different application case. So let's go with the problem. So as several previous presentations mentioned, in the field of remote sensing, we have a massive amount of data and we have a lot of satellites capturing a lot of images on an everyday basis, but labeling is limited. Like the pace of labeling cannot cope with the pace of acquisition of data. And not only that, labels can become obsolete. And not only that, the data is very variable. And even if we have some models training certain data, it doesn't generalize well to the other types of data. So here I show some examples of variability of images and sensors that use in remote sensing. So for example, we can have temporal variability, where in different seasons, the satellite images simply show very different things, like during summer and during winter with snow. Or we can have geographical diversity, where we have residential areas that look very differently in different countries, different continents. And then there are differences that come from using different sensors. For example, we can have sensors of different resolution, high and low resolution, and then the same length cover will look very differently. And also, we don't use just RGB images. We can have a different type of images with different number of channels, like, for example, multispectral, hyperspectral. We can also have SAR images. So all of this introduces domain shift between different remote sensing datasets. And today, I will mostly address the problem of images with different resolutions. And in the end, I will mention something about the current work that we are doing on images with different number of files. So since we have domain shift prevents us to generalize well and to reuse the models. And to overcome this domain shift, we can use domain adaptation. So domain adaptation is learning from one data distribution that is labeled, that is called source. So here we have labels, we can train classifier. And we want to apply that to other domain that we call target, that is either completely unlabeled, we don't have any target label data, or we have some small amount of labels, and we call that semi-supervised domain adaptation. So basically in domain adaptation, we have different distributions of input, but the same learning task. As here, for example, as you can see, we have the same objects, but in different environments, so that produces different distributions, but we still want to classify the same objects. Domain adaptation methods can be split into homogeneous and heterogeneous. So this division is very important in remote sensing because of these different types of images that we can have. So in homogeneous, this is when source and target share the same feature space. So the images are the same. Let's say they're all RGB with same resolution, but the domain shift comes from the seasonal or geographical reasons. And we can have heterogeneous images where source and target come from different feature space. So here we have different sensors, for example, different resolution, or we have completely different dimensional domains. So basically in homogeneous domain adaptation methods, we mostly care about minimizing the distance between domain distributions. And this can be done by reducing certain distance like MMD, which is mostly used, or we can do that in an adversarial manner. While for heterogeneous methods, here the most successful ones were the methods based on cyclogram. There are several different methods that try to translate between these different modalities. And also there are some other translation methods. And then there is also a domain invariant. There is also a method that extracts domain invariant features, which is the work from my PhDs, where we have separate feature extractors because we might need to work with images of different dimension. And then we try to extract domain invariant features by using adversarial learning. And this method showed strong semi-supervised results. We could achieve good results with just few labels, but it remained limited in unsupervised setting. simply because when we use different types of images, the domain shift is large, and we can have even if we manage to overlap the domains, we can have class flipping. So this problem remain. So we started with the hypothesis that if we use foundation models that are trained on vast amount of data and different types of data, that we can achieve a better domain generalization. But the main hypothesis that we have is that if we make representations of images more semantic, that we can enhance the class alignment between domains. And one example of injecting semantic information is using text. It can be something else. It can be dictionaries or it can be graphs. But language is very convenient nowadays because now we have very powerful language models. So we were thinking about using visual language models for this because they already show strong zero-shot classification performance. So we hypothesized that they can improve unsupervised heterogeneous domain adaptation data, which was so far difficult task to solve. So we will focus on the case of different resolutions. We will have RGB images, two domains that are RGB, but of different spatial resolution. As for visual language models, so we can have clip-like models like we saw in the previous presentation, but we can also have visual language models that are coupled with an LLM. So, for example, one example is Lava, where we have a vision encoder that is connected with a LLM through the projector. So, like some kind of network that is in between, that is transferring the data from vision space to the token space. At the same time, we can give prompts, we can give instructions at input, and we can fuse these textual tokens with image tokens, and then the LLM can generate answers to the question that we ask related to the image. So this is all nice, but the trouble is that the general purpose VLMs have limited performance in specialized cases. General purpose, they work very well, but if we want to use it in remote sensing, they're somewhat weaker. But again, luckily, there are many specialized remote sensing models that were started from these visual language models and were fine-tuned on remote sensing data. So we decided to try one of the existing models, which is called LHRS bot. So this is a visual language model trained on RGB data on high-resolution images. And here, as you can see, so here we have a vision encoder component that is based on SIGLIP architecture, similar to CLIP. We have LLM, and in between we have one component that is a vision perceiver. So let's say with an advanced projection layer that will take multiple layer outputs and fuse them to have a rich image embedding. And this was used for solving classification, visual question answering, visual grounding, and for RGB images of high resolution, it worked quite well. So we started from here, and we wanted to extract features from our datasets, both on visual level and textual level, from LLM and from vision perceiver, and apply domain adaptation on these extracted features. So first, to show you how these extracted features look like. So let's say, so to the right, we can see the source domain representation, and to the left, you can see the target domain representation. For source, we use the RASIS, which is RGB dataset, and for target, we use Eurosat RGB version, where we can see that like we expect for RASIS that is already fine because it's high resolution dataset, but for low resolution, which was not really used for training of this model, also representations are promising. So for domain adaptation, just to prove the concept, we use something simple. So we just used done adversarial method just to see if we can bring any improvements to zero-shot performance of the model. Since we already since we can get the same dimension of the features, we can use this homogeneous model because the LHRS bot largely accounted for heterogeneity between domains, so we didn't need to use some specific algorithm for heterogeneous domain adaptation. And we evaluated on these datasets. So we had RASIS and Eurosat RGB. RASIS is high resolution aerial, and Eurosat is low resolution satellite dataset. They have different resolution, and also you can see we extracted 8 classes that are corresponding, and you can see that some classes have very different representations, that it is not an easy adaptation task. So it's not just the resolution, it's also acquisition conditions are very different. And so we classify land covers, we do patch classification, level of patch. So For unsupervised domain adaptation, we do from RASISC to Eurosat. LHRS bot included RASISC while training the VLM, and we also use it to train a classifier part of domain adaptation method. So our baseline is the model without semantics, HIDA, that I already mentioned, which achieved 43% of accuracy. Zero shot made a big improvement, like 20% higher accuracy. And then the rest of the results are based on features extracted from vision part and from vision encoder and from LLM. So the first two results are also baselines. We train a classifier on source features and apply it on target features without doing domain adaptation. So this was a bit weaker than zero shot, but just to provide a baseline. And then we took features and coupled with done. We did separately for vision features and LLM features. And this made a large improvement over zero shot performance, especially over the previous result that we had with HIDA. And we achieved almost 90% of accuracy, which was very surprising that it made such a big difference. We knew that it will be, we suppose that it will be better with semantic data, but the result really surprised us. Then for semi-supervised domain adaptation, so we experimented in several cases with several labels per class, and with 5, 10, and 25 per class out of 400 that we used in the training set. For this, we use as a baseline semi-supervised version of HIDA method. And as you can see, when we have a small amount of supervision, then we can still make a big difference between LHRS bot, between VLM and HIDA. While domain adaptation, it's still making some difference, not as much as before, because we already achieved high performance with this supervision. And as we go further with supervision, zero-shot approaches domain adaptation. There is less and less contribution from the domain adaptation because we can already achieve high result with the labels that we have. Regarding the current work that we are doing, now we are so just briefly, we are saying about we are doing with different channels. We are evaluating RGB and multispectral and SAR. The trouble, if we're going to different modalities, is that there is a scarce work on multispectral VLMs. There are not much methods. And if we try to use representations from them and combine with RGB VLMs, this proved to be a challenging task. And also what happens is that we managed to construct one pipeline without domain adaptation, where in unsupervised manner, we can already reach around 90% accuracy using zero-shot pseudo-labeling, student-teacher. And it turned out that domain adaptation doesn't contribute over this. It cannot do better than this. So we will see if we will exploit some more difficult tasks to see if domain adaptation can still, heterogeneous domain adaptation can still contribute, or to go with a smaller domain shift, because here we have difference in channels, difference in resolution and acquisition, so it might be more difficult. And we are also working in currently new multispectral dataset, so that we intend to train our own vision language models. So this is just a small insight into what we're doing at the moment, but this is all work in progress. I don't have results to show on this part. So I thank you very much for your attention.
Are there any questions? We have time for one question. Yes.
Yeah, sorry, just in the single shot report, there is a vision treatment which you are using.
Yes, so I'm using the model that is called LHRS bot. For vision encoder, they used SIGLIP architecture. And then they invented their own vision perceiver architecture, which takes output from multiple layers and fuses that. And then for LLM, it was Llama 3.
All right, thank you.
You can move on. Thank you once again.